have a great meeting, and I would now like to introduce the chair of the first session, Bill Farrell. He'll talk a little bit about what the first session will be about. It'll be basically, the theme of the day is science investigation, science concepts, and mission concepts involving CubeSats. And Bill is, in addition to being the PI of a proposal that he will be talking about that we just submitted for the H-TIDES program, which was an opportunity to compete for one of the EM1 slots that the Science Mission Directorate at NASA has on the EM1 mission, but on the EM1 CubeSat slots. But in addition to that, he's also the, among other things, the head of the DREAM team, which is one of the survey nodes. And this is basically the second time around for the DREAM team, very successful team, and of course I'm on the team. So I would like to, without any further ado, and turn the program over to Session Chair Bill Farrell.
All right, thanks, Pam. Thanks so much. Very kind introduction. So I guess I'll stand up here. I just want to say a few words about what this session is about and why you would have science. It's really a science-enabling technology, and enabling technology CubeSats are. So why would you lead off with science in the first morning? And there's two reasons I can think of. At a very tactical level, science helps drive individual missions. Identifying the science requirements. There are many possible drivers for missions, but science requirements for science missions help drive the mission architecture, the mission design. But there's actually a strategic reason as well, and that is for talking about science here, and that is really our buy-in for science missions in planetary has gotten so steep with the Discovery program. That's really our first quantization step size, if you will, of getting anywhere is $500 million. And the thing is, there's a lot of science, particularly at the moon, right nearby, that can be done, and with less expensive packages and less expensive payloads. And so that's really, I think, one of the great possibilities for CubeSats. And actually, people are realizing that with this EM1 mission flyby. And as we get more and more of these opportunities, possibly at Europa, they might drop CubeSats. Phobos and Deimos. As you get more and more of these opportunities, we'll get to make the technology better with each one. I heard earlier that the success rate's about 50%. All right, but you're not losing a discovery package, right? A discovery mission. You're losing something not quite as expensive. So maybe we can build more with the idea that there might be some losses inherent. Anyway, so I just am real excited about CubeSats in general. So this morning you're going to hear a set of science-oriented talks. Mine, as Pam said, is about a proposal we just submitted in the last month to the Heliospheric Division. The talk after mine is by Friedman Hood. He'll be talking about the very interesting search for water at the moon, which really has really kind of taken storm in the last 5 years or so, following some IR observations that hydroxyl could be buried into the lunar soil, a lot more than people initially thought about. So I'm very interested in your talk. I'll be taking notes. After that, Bob McCall will be speaking about CubeSat applications in radio astronomy, and in particular an interferometric array, which actually is really interesting. And I know he's been working with the teams at JPL and NRL on this for probably over a decade. And and CubeSats again offer another possibility of a small platform, which they've been looking for a long time. Dan Schill will be talking about geotechnical properties of materials from CubeSats, and I'll be very interested to hear how that is done. Then tonight there are a set of posters, a whole set of really interesting posters. One I'll call attention to in particular is Mike Collier's on using an X-ray imager to study the lunar exosphere, the gases given off by the surface. And a number of great posters. So it should be a fun session. I think it's very diversified. And in some senses, it's as diversified as the ideas that pop up in each of our member in our community. So you'll hear, so it's hard to integrate it all because some of them are very disparate. But in fact, as more and more opportunities to fly to the moon occur, we'll have more and more opportunities to kind of canvas across the community for new ideas. So let me start out then. I guess I'll start with my talk, and I'll go to the beginning here. I think I'm looking at that slide for a while here. During the summer, the Heliospheric Science Division actually sent out a solicitation for a CubeSat to be dropped off during the EM1 mission. Now, the EM1 mission was launched in 2017. It's a human exploration. HEO's second test of the Space Launch System, the SLS, and the Orion. There are actually 11 slots on a booster stage for CubeSat opportunities. At this point, there's one assigned slot for sure. There's 3 human exploration HEO slots, and possibly a number coming out through the space technology, the new space technology director at downtown. And our particular proposal is called TerDLE, Terminator Double Air Explorer. And I'll tell you more about what a double air is as we get going along here. We have a number of expert partners, including Catholic University and Morehead State and George Washington. Well, really what we're studying is something called a lunar wake. And actually, what people may not know is that the sun actually gives off an ionized gas called the solar wind. It's actually very low density, about 5 particles per cubic centimeter. For comparison, a cubic centimeter of gas in this room is about 10 to the 19 particles. So you're talking 5 particles per cubic centimeter that flows out at about 400 kilometers a second. Now, this solar wind, the moon actually acts as an obstruction in the solar wind. And on the other side of that obstruction, you get a trailing wake. You can think of it like a bow wake, or from a boat. And so you actually disrupt the fluid. And in fact, right behind the oops, let me just go back here. Right behind the moon on the anti-solar side, it's believed that you get very, very low densities, and early models suggest it's even a vacuum back there. So the question we've had is how does the plasma expand back in behind the moon there? Now, early on, in the early 70s, it was believed with spacecraft like Explorer 35 that you actually had a complete discontinuity, that you'd have plasma on one side and almost a pure vacuum or pure vacuum on the other side. This is called a tangential discontinuity that would extend back about 4 lunar radii or so, 4 to 5 lunar radii, to then form a shock right here. Hope you can see that. I think a little tag comes up when I do this. And this model persisted for about 20 years until about the mid-90s when the WIND spacecraft went through the wake with modern instrumentation, modern plasma instrumentation. And what they found there is that both ions and electrons, and I'll show you some data here. Actually, I probably shouldn't show data, but I'll show data anyway. Shows the solar wind, shows the ions and the electrons getting right into the wake and flowing in. And in fact, some instruments even saw ion beams moving across the wake flank, moving right into the central wake region along magnetic field lines. So this is a very different picture than this perfect discontinuity that was talked about earlier. In fact, this picture they call an ion sonic wake, and similar to the kind of the wake that's trailing the space shuttle. And I had some experience studying that in the mid-'80s. Now, Lunar Prospector in the late 90s flew around the moon at around 100 kilometers or so and got over 6,000 passages, but only had electron data, not ions. But clearly the electrons got into the wake. They were like they were less than 1% density. And what you're looking at here is a latitude versus longitude, where longitude, 180 degrees longitude here is on the anti-sunward point. So you're basically looking down the cylinder. Back trailing behind the moon. And it's very consistent. You can see this really nice picture when you integrate up these 6,000 passages where you get this density drop to below 1% from solar wind density values. You also measure a cross-flank electrostatic potential on the order of about 300 volts or so. So clearly the picture is that the plasma does get in there, although it's at much, much lower density. So the question that we're asking on the TerDLE team is what happens right behind the obstruction, right behind the Terminator. And if you stop and think about it as an experiment, initially right behind the Terminator where the plasma is initially obstructed, you would expect there to be a perfect discontinuity. And if you look at the old theories, it would say the discontinuity went out 6 lunar radii. We know that it now fills in, but there's 2 different views on this initial expansion. One is that it remains a neutral expansion, that electrons and ions kind of move in together in sync. But other people studied fluid flow in plasma fluid flow in these expansions. Actually, some real early work suggested that you actually lose neutrality, that the electrons are able to move in, since they're lighter mass, move in ahead of the ions. And in doing so, they form what's called in plasma physics is a double layer, where you have electrons spatially separated from the ions to create a fairly strong electrostatic field. And this may kickstart the initial expansion. So what we're really interested in is that kickstart, what is that kickstart in that initial expansion? We did, over the last few years, you can tell this is something I've been working on for a while, because I love this stuff, is over the last few years we've actually done a set of simulations which clearly show that you get this expansion of the electrons moving in ahead of the ions. And here's an example, whoops, let me go back up here. Here's an example where the electrons cloud, this electron expansion is ahead of the ion front, kind of like that schematic from a simulation we did back in 2008. And you get a strong electric field, so I blew up that region there. So this is the difference between ion density and electron density. So one of the questions we're asking with TerDLE is, fly through with a CubeSat, could we fly through this region with a CubeSat and determine neutrality as we get closer and closer as we spiral in behind this obstructing into this obstructing region? So here are our science objectives. Identify any plasma expansion density anomalies at low altitude near the Terminator. Assess the solar wind's controlling influence. There's an interplanetary magnetic field, and that might change direction. That could affect this structure. And so we want to have a number of events under varying conditions to see if this non-neutral region changes configuration or disappears. Then the last one is to determine if plasma neutrality is just lost. Who's right, the Crow and all picture or the Samir, which would suggest that neutrality is broken, or the Samir and all picture from '83, which maintains neutrality. Now, of course, the mission requirements that you would want on any CubeSat is that you have paraseline. Paraseline is like periapsis, only at the moon. At low altitudes in the vicinity of the Terminator obstruction point, really right behind the Terminator. The orbit have a progressively reducing or decreasing paraseline. Really, ideally, you'd love to have it crash just after going through paraseline so that you're at the lowest altitude possible. We need to be able to point an ion spectrometer into the flow to get a density measurement at least once every 10 seconds. That is no problem meeting that mission requirement. And again, you want to stay up long enough and spiral in over time to look at this structure over long periods. We have no preferred, no predefined inclination. That's what's nice about the Terminator. Terminator is sort of an annulus around the entire moon, so and you cross it. You don't need to get into magnetic anomalies into very exact spatial locations. You're going to hit the Terminator. As long as you don't crash in, you're going to hit the Terminator twice in orbit. And so it's automatic science for us. So here's the team that we assembled, our expert partners. Now we'll have to say, this is where meeting like this is important. This is where we meet these expert partners. Pam had these connections in the community in particular. So we're out of Goddard, we're leading it, but we teamed up with the folks at Morehead State, Ben Malthus, and the folks at GW who helped provide propulsion, Michael Kiter. And we have and also using Blue Canyon technology with the microthruster, kind of a new mix there. On the instrument side, Mike Collier down the hall has a nice ion spectrometer, and we build plasma waves in our lab, so those are our primary instruments. But the big thing that we have on this team that I think is really important is a mission design team that has just done a super job matching our requirements to what the 5 minutes to what we can really do. Here's a CAD of everything packed into this 6U payload. I show our block diagram here. This is a random stack of our resources. I'm not going to go through everything, but if you added up all the masses, you're going to get 6U. If you add up all if you add up all the masses, you're going to get 12 kilograms. If you add up all the volume, you're going to get 6U. The spacecraft has 72 watts of power. If you add these up, we actually have 90, but in fact, propulsion is the tall pole here. You can see that it's right there, 47 watts. But we don't use propulsion all the time, so we have modes, a propulsion mode and a science mode, and that way we stay under the 72 watts. One of the key challenges we had here, and this is where that mission design team was so important, was to match our lunar capture requirements with the micro thruster design. The thrusters alone couldn't get us directly into lunar orbit, but Dave Folta and the mission design team found that if you actually could get a little bit of acceleration here in the early part, about less than 20 meters per second, and then you would hit the moon about 6,000 kilometers above the surface, you can actually do a set of swing bys that gets you into capture, and actually using the Lagrange point out to the extreme left of the figure here to kind of arc around. And then you can then do thruster firings over time to get yourself into the science orbit. So in essence, we're trading time for low thrust. And just to show you that we make these, we have, this is actually a pretty robust solution in the sense that there's lots of different ways of implementing this. And in fact, I show 3 options here. But with just 600 micronewtons of thrust, which the GW micro CAD thrusters can provide, you can achieve these orbits. So that was one big thing, was to get the mission design, the orbital design, and the propulsion technology to match up, and it did. I kept expecting it to not work, and Dave Folta kept going, "Hey, we can keep doing this." I'm like, "Oh, Dave, this is amazing. How can you do this?" Now, our instruments, of course, we have an ion spectrometer, and then we also have a plasma wave system, which measures. Ion spectrometer gives you ion density. The plasma wave can actually get you not only waves, but can get you the electron density by looking at the Langmuir waves. So these plasma oscillations, these narrowband radio waves, really plasma waves, in some sense the medium is calling out what its density is by looking at this particular feature, this Langmuir wave, which can be sensed, and you can obtain the density that way. And so we need plasma wave antennas, which you can see down at the bottom there that we've included, 30 meters and up and 130 meters down. Our methodology, of course, is that we make multiple crossings. We'll do exactly kind of what we did in these simulations. We'll get the density, electron density and ion density, and do subtractions. We'll look at the slopes. There should be, there should be a ULF, electric field increase, as we cross through this ion minus, where you go from ion rich to electron rich. That's ion rich in green, electron rich there in blue, when you cross the double layers. So finally, I'll just say that, oh good, okay, so I got 2 minutes. We're going to have our proposal is to employ a 6U CubeSat. We want to get into the Terminator low altitude regions, parasaline, using low thrust and an indirect orbit. Our primary objective is to get that early expansion time, just behind the obstruction, to figure out whether the initial expansion stays charge neutral or whether it's a non-neutral double layer. And finally, the way we're going to approach this is get density measurements over many crossings. But on each individual crossing, we'll get ion electron density profiles, their slope, do differences, and look for those unusual features. So that's it. Let's see. There's one question here. Let's see. Okay. Okay. Now it's time for questions.
Myself on here. Okay, great. Are there any questions? And wait for the mic. Please wait for the mic.
Hi, Eric Dahlstrom, International Space Consultants. When you say low orbit, how low are you going to go?
Well, yeah, we're going to get below at least 170 kilometers, less than 0.1 RE, but even lower. I mean, ideally, and we worked out, depending on exactly when we launch and when we start doing capture, what we're really hoping to do is to take our last swing by as low as possible, tens of kilometers before we crash in. So, I would love to get that near source region, just get as low as we can. The idea is ultimately we will crash and get that data, and burst it back before we crash in.
Yeah, Warren James, V Infinity Research. How long will it take you to go from initial injection in Earth orbit to finally being in your science orbit around the moon? Yeah,
it looks like a couple 100 days. 180 days is what Dave said, but it also depends on our initial thrust and how much we thrust during the outer part of the orbit.
Hi, Chris Craddock, Rocket Star. who are you planning to use to launch the satellite into low Earth orbit?
Well, yeah, I should mention more about that. The EM-1 spacecraft actually has a cryogenic stage, and that cryogenic stage will actually have 11 slots. And I should have said more about this. There's actually 11 slots on that EM-1 mission. 3 of them have already been defined by Human Exploration Mission Directorate. Science has at least 1 slot and may get 2 more. The science is out of NASA. And then the Space Technology Program wants to take up the other slots. So we're actually going to be a ride-along on that EM-1. It's really a test of the Orion capsule on the Space Launch System in 2017. So yeah, so the hard part is they're doing a lot of the hard work for us.
When you present this idea of going and studying the plasma, how it expands, what effect would you have if the plasma changes as a function of time, because the sun is spitting out different intensities? Exactly.
That's why we have to get multiple crossings over long times. Then we do a correlation of that. Like, you know, the IMF, the Interplanetary Magnetic Field, if it actually starts pointing down the wake rather than across the wake, that might change the nature of the structure. So what we want to do is correlate those features using a large set of crossings.
Glenn Cameron, Maryland Aerospace. For the kind of science you're doing, you're going to need really good electromagnetic cleanliness. Have you established requirements for what the fields and waves and stuff have to be?
Yes. As it turns out, we have thought about that a lot, primarily because we're using the microcad thrusters are themselves, you know, they're going to disrupt the plasma. They're creating a plasma. So, yeah, so we plan on having very strong EMI, you know, testing and examination. One nice thing is, at least on the plasma wave system, the radio wave system, that Langmuir wave is a disturbance in the plasma, and it's one of the most intense plasma waves. And as long as we keep that as our primary science objective, and don't look for real weak waves, but look for that primary wave, we can actually live with a fair amount of noise in our environment, you know. But if we were going for some weak plasma wave signature, I agree, we would really have to balance it more. But that Langmuir wave, though, is so disruptive. It's the whole plasma oscillating like this. Your whole environment is just, you know, and that's really helpful. It's the noisiest thing. Actually, it sets the automatic gain control for most spaceflight radios, that scientific radios out there. You know, when they want to look at, you know, weak Jupiter events, they have to find a way to filter that Langmuir wave right out of the right out.
Warren James, the Infinity Research again. On the EM-1, when you're released from the spacecraft, what sort of an orbit are you on at that point? Is it would that take you to the moon already?
Nope.
You know, what's
nope. In fact, I should have mentioned. I've done more to say that. Yeah, no, we're actually all right. We're on an escape speed. We're hyperbolic. And that's one of the reasons why we have to do this convoluted swing by of the launch point, you know. So and then if we do that and do a long but a low thrust but over long term, we will eventually come back into to get captured. This is what they did with the Artemis spacecraft, for example. But yeah, initially we cannot directly get in. In fact, if we just stayed direct, we just go off into, you know, oblivion.
Heliocentric trajectory.
It's a
basically. Right. So it takes a lot of delta V just to slow down enough to be captured by the moon, or clever tricks with low energy trajectories. And by the way, Dave Folta is giving a presentation at this meeting, and he will talk about some of the work that he does to come up with these low energy, low fuel expenditure trajectories.
All right, that was a key challenge. Unfortunately, I didn't build it up enough. But yeah, they just dropped it off, we'd be gone.
Thank you. I think we're ready for the next speaker. However,